In talking about fluid dynamics, we've talked mainly about Bernoulli's equation, which is what this segment of the class is about. We've formulated it in one of these two forms, which is the integrated form, if you like. We know that this part and this part are force, and this is mass times acceleration in Newton's law. We haven't worried about these loss terms, and we haven't cared about this pump term, but we've talked about writing it between upstream and downstream. We have a similar equation where you go perpendicular to streamlines instead of along streamlines. And we've talked about the sign convention for that. We used it for a big bucket with a hole in it, the so-called free jet equation, which is really the same expression as the acceleration or the velocity of a particle that you drop. So if you drop a ball from some height, the velocity it will travel at is actually this velocity. It's no different from that. And so that's why we can think of water as a series, if you like, a bucket full of balls, of which the balls are falling out, and this is exactly the same velocity as if we dropped a ball from this height starting at velocity 0. By the time it's h below my hand, the velocity it'll be traveling at is this particular velocity. Nothing more than that. And the other thing that we talked about was that sometimes if we're trying to solve Bernoulli's expression, we have 6 unknowns, and we can solve it if we only have, we have 6 quantities, and if we have only one unknown, we can solve for the remaining unknown. If we have 2 unknowns, then we can invoke something else, which is volume in equals volume out. And this is a consequence of the fact that between 2 streamlines, a stream tube, if you will, the entry into that and the exit out of that is the only place that fluid can flow. And so since fluid can't flow across a streamline, then it's confined in that duct, that stream tube. And so anything coming in at the upstream has to leave at the downstream if you're not accumulating things. Because if you're accumulating things, then the velocity or pressures have to be changing as a function of time, which would be violating Bernoulli's law. So that's kind of a recap of where we were. And so we started last time to talk about why we want to, one of the ways in which we've used Bernoulli's law, and that is to be able to define flow velocities. We applied it earlier on to a pitot tube for aircraft, of course, which is an ultimate application of this. But a much more mundane application is to apply it in pipes, where you can measure velocities quite easily. Sorry, you can measure pressures quite easily and use those to calculate velocities. And so robust measurements of pressures are easy. Measurement of velocities is much more difficult with, say, a spinning impeller you could use. It used to be on gas, when you pumped gas, you'd be able to see coming out the tube at the side of the gas pump, there'd be a little circular paddle. And the circular paddle would have a pivot through it. And if you think of just a single paddle that would rotate, that wouldn't quite get it there. But if you think of a paddle that would rotate around a pivot and one at 90 degrees to that attached to the same thing, this would actually flow around as you basically metered gas out of the system to be able to measure the volume that you'd get. Because obviously, if you're paying for gas, you might like to get the correct volume as you pay for it. And so there are other methods of doing it, but pressure measurements is actually the easiest one because you don't have any moving parts. And that's one of the joys of it. We talked about it last time briefly. So today we'll talk about flow measurements both in pipes and in open channels. So stream flows, how you measure flows in a river, for instance. And we'll talk about some of the limitations of Bernoulli in terms of when we can use it for compressible fluids. We've talked a little bit about the spatial reference frame in the guys from the bike. The fact that if you're doing Bernoulli for a bicycle, maybe you don't choose to have the bicycle run past you where it's not steady state, but you have the bicycle static and you have the wind blowing past you. And we'll also talk about another violation of Bernoulli, which is not steady flows, to solve problems which aren't steady, which you can use it for as well. So that's kind of an outline. So we'll put Bernoulli to bed today, I think. Talked about this last time. The idea of a Venturi constriction is that you constrict it. Since you constrict it, you know that the velocity is going to have to increase from point 1 to point 2 because of V1 A1 equals V2 A2. So if this has to be constant, then if you decrease the area, you have to increase the velocity. If you increase the velocity at this downstream point and the total magnitude of Bernoulli has to remain the same, then increasing the velocity, if you're at the same elevation, has to decrease pressure. And so it makes sense that that's exactly what's the case. If you increase it large enough, then you can cavitate it because you decrease the pressure below the vapor pressure. And so you probably want to avoid that. And you can imagine the constrictions that you'd apply could be from the most rudimentary of basically putting a washer across the flow to putting a curved washer across the flow to actually taking a modification in the pipe and being able to modify that. Actually, why don't we look at, you perhaps are tired of listening to me. Don't blame you. See if this will... I don't hear that. It's so this is a commercial advertisement for people who make
the most diverse substances are transported and distributed in piping systems every single day. They can include solvents and chemicals, oil and gas, or steam for energy transmission.
And so they're just making the case that blah, 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 you can use it to be able to measure...
The fluids flowing through pipes often have completely different properties.
Flow rates in pipes,
therefore,
which is what
different
their
principles for their measurement are required.
Impression, hopefully,
one
of what a
method is flow
Venturi
measurement, based on the differential pressure principle.
See if they do the cutaway.
Some 300 years ago, Swiss mathematician and physicist Daniel Bernoulli discovered the direct relationship between the pressure and speed of a fluid flowing in a pipe. Italian physicist Giovanni Battista Venturi also performed experiments on flow. And in 1797, he built the first flow meter for closed pipes, known as the Venturi tube.
And let's see if they do a cutaway. Hopefully they will.
Here is how this measurement method works. Differential pressure flow meters have an artificial restriction integrated into the measuring tube, illustrated here by the example of an orifice plate.
Venturi, of course!
Two holes are located in the pipe wall, one before and one after the orifice plate. Two separate tubes connect these holes to a differential pressure
think about the last exam. Think about the next one.
Think about pressure changes separated by a diaphragm. The tiniest pressure differences in the flowing fluid can be precisely measured. If the fluid is not flowing,
it's just a constriction
pressure
that allows you
before
to be
and
able
after the
to measure
orifice
pressures at
plate
these 2
is
points,
essentially
upstream
identical.
and downstream of this.
As soon as the fluid starts
here,
to flow, its velocity around the orifice plate increases significantly because of the restriction
the more graded
in the
transition is, the fewer eddies you'll have, the less separation you'll have in the wake of this,
the static pressure
and the better
at this point
measurement you have.
decreases.
I think these are inserts.
Consequently, different values are
so the other thing
in the
is
pressure
that
chambers
the
of the
point we made
sensor.
last time is that
A
really
higher pressure
the only
before
measurement that's important is the difference in the
after
pressures,
the
not the
orifice
absolute
plate.
magnitudes of the pressures, but the
This
differences
pressure
in the pressures.
difference is a direct measure for the flow velocity,
uniquely
and thus
defines
the
the
mass
velocity
and volume
from
flow
our
in the
friends,
pipe.
Daniel, what's
the higher the
Venturi's
flow
first name?
velocity
Enrico Venturi,
and the
something
resulting
like that?
drop in pressure around the orifice plate.
For now, okay. So the expression comes then from writing the equation at 2 points, upstream of the Venturi constriction, downstream of the Venturi constriction, noticing that in this we have two values for velocity, which we can link if we write them in terms of being the volumetric flow rate. It's the volumetric flow rate because it's an incompressible fluid in this particular case, so we don't have to care about density. You could multiply, of course, both sides by density if you wanted to, and then this would be the mass flow rate. But if density doesn't change between upstream and downstream, we don't care about this. And if you write, say, what would we write? If you write velocity 2 instead of in terms of velocity 1 and substitute it into this expression here, I guess actually if you write velocity 1 in terms of velocity 2 and substitute it into here, then you can rearrange this expression and you get this. So this would be a velocity, this whole term here, at point 2, multiplied by the area at point 2 just gives you a volume flow rate. And so you notice that all we need to measure is the values of the differential pressure. And so you can measure it either with a pressure transducer, a differential pressure transducer, which just measures the difference in pressures between two locations. The advantage is that it has a very small range. And so if you were measuring 101 kilopascals and 102 kilopascals, the range you need only is 1 kilopascal. And if you have 500 kilopascals and 501 kilopascals, then the range you have again is only 1 kilopascal. And so if you're using a differential transducer that maybe measures only over a 3 kilopascal range, you can get a very accurate measurement. If you have individual pressure transducers that measure between 0 and 500 kilopascals, then the resolution you'd have of that differential pressure is much less. And so you can measure it with a differential pressure transducer, which measures just the difference in two pressures at two out ports in the system. Or you can measure it in terms of using manometers. And so there the system is roughly the same. You could measure the behavior upstream and downstream of the constriction, whatever that constriction is. Or you could measure them in some complicated way like this one. So I thought we'd just go through this just to see how we'd solve it. We have flow in a pipe. The pipe changes diameter as you go downstream, so you should be able to use this change in diameter to be able to measure the velocity of flow, the flow rate in the system. But instead of measuring with pressure transducers, you measure it with a manometer. And so how would you go about doing this? So there are probably three concepts, I guess, which you have, which you'd need to apply. One is that you can write Bernoulli between point 1 and point 2 to be able to solve for these two velocities, just like we did here, like this. The second is that you might need to use the fact that you know the cross-sectional areas at these points to be able to solve for the fact that the flow rates have to be the same at points 1 and points 2. So you can write Bernoulli's expression. Let's see if you need anything else. And so if you use Bernoulli, you can write the expression at point 1 and point 2. What do we have? At point 1, we measure a pressure in this pipe somehow. So we have a pressure at this point, which we think is represented by the other behaviors in this manometer tube, which is stagnant, by the way, right? There's no flow through this. We have a velocity at this point, which is stagnating. You could choose it up here, in which case it would be a finite velocity, or you could choose it right in the maw of this tube, in which case it would be 0. And the elevation of these 2 points are the same, so we can probably just get rid of those two. We have another pressure down here, which we're presuming that this measures some component of. Of course, the tube could, if you like, come to this point, so long as it was flat-bottomed. But you can also get the pressure just from going directly through this tube to this point, just vertically in the fluid. It doesn't matter really if it's moving. The velocity at this point, which we don't necessarily know. And the pressure at this point, which we can hopefully measure as a function of this. So actually in this case, the fact that you're killing the velocity off here helps you, because now instead of having two velocities, for which you might want to use this to resolve the difference in them, probably you don't have to use that. So I lied. You need Bernoulli's equation. Perhaps you don't have to apply continuity to get it. If you rearrange this in terms of the pressure differences that we hope we can determine, you get it as a function of the velocity in the pipe. And of course, if you want ultimately to get the flow rate at point 2 rather, not point 3, is just going to be equal to the area at 2 times the velocity at 2. So if you can get this velocity, you're golden. So that's the first part. Well, the other part is to be able to figure out exactly what the fluid pressures are within this system as well. And so what we could do is you can write the Manometer Equation. And so the easiest way to write that, they have the expression here, but the easiest way for me is the pressure at point 1, and just work your way through here to point 2. So the pressure at point 1, if you go up, bless you, L times, this is water, L times the unit weight of water, gets you here. Simply connected fluid gets you here, across here. So to go up to this point here, okay, you're not helping me, are you? This is negative, this is minus, right? Pressure here, you go up, you subtract, you end up here. Simply connected fluid, you end up at this point here. Bless you again. You can go up another 4 inches, and that's subtracted. Minus, I guess, H. I think this is 4 inches equals H times the unit weight of the gauge fluid, which I think is mercury in this case, but not sure. And then you end up at this point, and then you have to come down all the way to this point. And so this is going to be H plus L. Okay. And that has to equal the pressure at 2. And so you could, for instance, subtract this off, in which case you lose this. You could make this negative, in which case you get this. And then, since you have this written in terms of this, you should be able to substitute it into here. So you have a pressure, you have it defined in terms of lengths and unit weights, which hopefully you know. I guess you can simplify it here, right? Or can you? This L times H2O should cancel out, right? This and this should cancel out. And I didn't go through this, but the bottom line is you can express P1 minus P2 as a function of lengths that you know, which is also equal to this, and therefore you should be able to solve for velocity. So I won't go through the math because it's in British units, and I don't know how to solve things in British units, but that's basically the gist of it. So in this case, Bernoulli, conservation of mass, and the Manometer equations allow you to solve it. Actually, the conservation of mass equation you don't need to use as a consequence, really, of this velocity here just being 0, so you don't have to balance these velocities to do it. If this was just a straight piezometer tube that didn't have this right-angled bend in it, but was just vertically in it, then you'd have a velocity here and a pressure, and therefore you would have to use continuity, I think, because you have 2 velocities in the Bernoulli equation, 2 unknowns, and you want to solve for one of them, so you just relate one to the other.
Conditions for continuity, the same conditions for Bernoulli's equation.
If you write the continuity equation in terms of mass, it's always true. So if you write the continuity equation as area 1, velocity 1 equals area 2, velocity 2 times density 2 and density 1, then you're conserving mass between upstream. So it could be compressible. Continuity equation can apply to compressible flows as well. But as we've seen, we've applied Bernoulli to air, which is compressible. You know, the cyclist is really a compressible fluid. So, I mean, you won't have to make that decision in the things you do. You can apply it to compressible fluids so long as the pressure changes aren't so great, I guess is the issue. Okay? So flow in pipes. So how you solve it is being able to measure fluid pressures. Flow in open channel flows is a similar idea. Again, let's look at this. If you go into the field and you want to measure the flow rate in a small stream, a typical way is you march into the field with a piece of plywood, which is 6 feet long, 2 feet high, with a box cut in it or a V-notch cut in it. You block the stream, a small stream that you have, and you just measure the height the water comes up in this either square notch or V-notch or circular notch, and you use that to calibrate the magnitude. So the idea is you block the stream off with this, and you measure this height within the orifice that you have, and you can use that to calibrate the magnitude of the flow through the system. You could calibrate it, I suppose, by putting a bucket on this side if you wanted to be able to figure out what the magnitudes are, or you can do the calculation using Bernoulli to be able to figure out exactly what that is as well. And so the way of doing that is that these could occur in slightly different modes. This is an Overshot Weir where you have coming over the top of it. You can imagine systems where you have gates on dams where you have you can raise or lower this blockage to be able to change the flow through the system to allow water into your tail races to generate electricity. But the solutions are the same. So this is a complete across-river blockage, except for this gap underneath, which might be the whole width of the river. Doesn't really matter. It has some width, B, attached to it. Could be the whole width of the river, or it could be a small rectangular opening. And again, you can do what we've done before, is you can write Bernoulli, upstream and downstream. So choose a convenient location, choose a point on the surface, or you could choose a point here just as easily, and choose a point on the surface downstream and write Bernoulli just in this. This is not the way I usually write it, with unit weight dividing these things, but the same equation nonetheless. Pressures upstream and downstream are 0 because it's atmospheric. Velocities upstream and downstream we don't know. We want this to be finite. Even you could probably get a decent result even if you chose this to be 0, but you can also choose it to be finite. And you can also look at the elevations of these points which you measure. This is what you measure upstream, this is what you measure downstream. So you have each of these, so you really only have one equation but two unknowns. So you have to write continuity to be able to solve it. If you write continuity in terms of the area, which roughly is this height times the width, this height times the width here. And of course, what you typically want to do is to make the fact that this elevation here is really quite close to this magnitude here. That might be an assumption you make further on. And if you then take care of, I guess, if you write this, V1 is equal to V2 A2 over A1, and substitute for this, that gets rid of V1, and you're left only with V2, which should be this. So you substitute this into here, and then mess things around to solve for the things you do or don't know. In this particular case, if the only difference in these cross-sectional areas is that, as you can see, oops, I'm not doing something right. This is just, A1 is just equal to Z2 times B, and A1 is equal to Z1 times B. So that's why you end up just with this ratio as a proxy, if you like, for these areas, because the widths are the same. I guess this would be where the whole width of the river is equal to B. If the width of the river is B, but the width of the opening was smaller than that, then it wouldn't look quite the same, because this is the assumption we've used here. But that's perhaps more complicated than you need to worry about. If you make these assumptions and solve for V2, then you end up with V2 that you can then post-multiply by A2, which is getting very temperamental today. There's a little button on the side that I must keep on pressing. So this is Z2B, right? Just this. And so you get this expression, which actually isn't very different from our expression before. And in the limit, if you take Z1 to be very large compared to this, so in other words, if you have a very small opening compared to a very high head in the system, then physically what that turns this into is that what would you do? If Z2 is small, then this term goes away, so this term is just 1. If Z2 is small, don't need that either, then we end up with just C1. And this is just the equation for this is a free jet, right? The velocity of a free jet. And so velocity of a free jet multiplied by the area is just the volumetric flow rate. And so perhaps it's not surprising that that comes out to be that. So it's not particularly complicated, but that's basically the idea. So that's for an undershoot gate. A little bit of blurb at the bottom talking about the fact that the magnitude of this elevation might not be equal to the same as this gate, but typically it's not very far from it. And so the corrections that you can use to make corrections for the fact that this vena contracta effect is in place. Of course, if you measure this height directly, then you don't have to worry about that. You can use that directly to calculate the flow rate. If you try and use this height of the gate instead of Z2, which you'd think would perhaps be a good approximation, then maybe you have to make a correction to be able to take care of that. And so corrections apply in those particular cases. But we're not going to worry much about that. Okay? So undershoot, overshoot is the same thing. You can use Bernoulli to be able to write. So this is what you do in a small stream. You just block it and you'd measure the height in the window. So you'd measure this height here that you have here within the window, which may be the upstream height or it may be some height below that. But you can use the same kind of analysis to be able to do that. You can look at a point here which would go through and come out at some location downstream. You could use a point here that would come out and go through at some location downstream. And I guess the critical feature in this is that there's some separation in this. So if you were wanting to be a daredevil and walk under Niagara Falls, you could sit yourself here and you could breathe just fine because there's this separation, there's not water circulating in here, it's just an air pocket. And so if there's an air pocket in here, then the chances are that this is connected to the outside. It certainly is if it's just a finite length, a long plank with a finite length box cut in it, then certainly air pressures can get to act in this location here, just from the side. And so this is atmospheric pressure at this point. And so if this is atmospheric pressure, then you expect this to be atmospheric pressure here. And so you could write a stream tube that would go from upstream location all the way through to here, where you know that you have atmospheric pressure. And actually, it's not very different from having something, if you think about it, that looks like this. It doesn't have this upstream component here, but you have a pressure here, you have atmospheric pressure acting at this point, and so the difference between these two elevations, which we've called in the past h, gives you a velocity v2 just from the free jet, is that v2 is equal to square root 2gh, right? You could do Bernoulli to do this, but basically we get this expression to be able to represent that behavior. So the velocity out of here is a function, if we think of this upstream part as stagnant, with no velocity, the velocity out of this point is going to be equal to square root 2gh, the same velocity as we drop our ball, interestingly enough. And the only thing that's going to change is that as a function of the geometry of this gate, whether it's a V notch or a semicircular notch or whatever, then there's going to be some correction factor added to it to be able to accommodate it. So we can calibrate it to be able to accommodate that. If we know the velocity, we can multiply the velocity by an area to be able to get a flow rate. And if we have a flow rate, then we end up with an expression to be able to define it in terms of gravity, some height of water in the in our orifice that we have. So this is some height in here, and as a result of that, if we know what this calibration is and we know what the width of our gate is, we can get flow rate. So it's just a matter of being able to define those behaviors. Okay. So we're just using free jets to be able to do that. Okay. So in pipes, we measure fluid pressures. In free surface flows, it's much easier for us to measure elevations upstream and downstream of an obstruction, but I think the process is the same. That's too complicated to worry about, so let's not worry about that. Okay? So those are typical methods of being able to measure flow rates in systems. The other concepts that we have is that we've talked about Bernoulli, and in cases where it's inviscid and there are no energy losses in the system, where the viscosity is assumed to be zero, then we only have this term. We don't have any extra terms in it. What we can think of this as, one way of thinking of it, is that the constant amount of energy that we have in the system can be defined in terms of the energy head, which includes all three of these terms. So potential, force, and kinetic energy, if you like, components at all points. And we can also look at the components which are due only to the hydraulic head or the piezometric head. So when you deal with fluid flows in porous media, then typically fluid flows in porous media, you can use Bernoulli. The velocities are really small. And compared to these other components, we just ignore the velocity squared term. And the other significant thing that you deal with when you're dealing with fluids in porous media is they're not inviscid. They actually have fluid losses as you go from where you're pumping something in to where you're pumping something out or recovering something. And that is taken care of in the permeability, which is the mechanism by which we accommodate changes, the loss of energy in the system as you go between upstream and downstream. So everything that you do in petroleum engineering in terms of Darcy's law, or in environmental systems engineering, or mining engineering, for that matter, or energy engineering that uses Darcy's law, it uses Bernoulli, it uses hydraulic head, and it throws away this term because the velocities are trivial, that they just don't make any difference. The velocities are small, so there's no inertia. So you're not accelerating fluids greatly. The viscous losses in the system are much larger than the accelerations you have in the system. And so you can use this concept to think of plotting Bernoulli between upstream locations, say in a tank that goes into a narrow pipe that goes into an even narrower pipe, whereas you go downstream between these three different locations, the energy head has to be the same. Bernoulli has to be the same if there are no viscous losses. If you want to look at how the hydraulic grade line changes, then this conceptualization allows you to take care of it. Upstream, everything is in potential head. There's no pressure in the system, no pressure potential. There's no velocity. As you go downstream, you've taken this fluid from being stagnant and you've accelerated it, so you've applied some velocity. So a portion of it is now kinetic energy, and a portion of it is this hydraulic head, which is the sum of elevation of the point and the fluid pressure that you'd feel at that point if you're sitting at point 2. And as you constrict it even further, then the velocity that you have in this particular case, you know that this exit point, the fluid pressure has to be 0, right? It's coming out, all of a sudden it sees fluid pressure, the air pressure rather, so the pressure here has to be 0. So de facto, the elevation can only be the elevation, and so the remaining portion of it has to be further accelerated to be a larger velocity. And of course you'd expect that from continuity because the area here is large compared to this area. The flow rate Q2, if you like, has to equal Q1. And the only way that can happen is if this is applied, and so if area 3 goes down, then velocity 3 has to go up because this is constant, right? Some magnitude. And so you'd expect now that this velocity has to increase. How much does it increase? Well, it has to increase all the way to 0 fluid pressure because we're exiting at atmospheric. And so you can use the concepts of the energy line and the hydraulic grade line to be able to accommodate those behaviors. And so this this kinetic energy term is what's present in the system. So it's one way to be able to look at these. So the other way to think about this actually relates to something that you saw a couple of nights, well, it's also related to the Venturi flume as well, is that you can make the same application to a pipe that goes along. The pipe has a constant diameter and goes between an upstream location and a downstream location. So you could write Bernoulli for this. You use Bernoulli to be able to calculate a flow rate that comes out of this, which is a given flow rate. But what you do know also is that the flow rate Q here and here and here all have to be the same. And so the energy line at this point would be for all three terms of Bernoulli, which would be this magnitude. This has to be true as you go all the way through this pipe. It's not violated. And so you can look at how the fluid pressures would change as you go through here. So as you come out of this pipe, you're accelerating the fluid, has 0 velocity initially. At some close place to the entry, it has some bigger velocity, which is up to the velocity that it would have. It has the same flow rate here, so the velocity isn't changing as you go. You could imagine, if you like, that this could be precipitous, right? It could be vertical if you like, and go along here, but the reality is it'll take a certain amount of length to be able to accelerate. And so as you go along here, the velocity is constant along this pipe, and so the component of the velocity head, the kinetic term, also has to be constant. This height here has to be constant all the way along here. And so you know that. And so if you look at a point here, then if this is the velocity term, this other part here has to be what we've called h. which has to be elevation head plus a positive pressure. But if you go here, then the pressure actually would be 0 because it's right on this line, because this now is the elevation. This is the velocity term, and so the pressure here has to be 0. If you go above this, then all of a sudden the pressure term has to go from elevation, which is above here, you have to go above here and in the wrong direction. So this would be in tension. This would be less than atmospheric, be subatmospheric. And so if this height was large enough, then you'd actually cavitate your water. And so the cavitation, the pressure vapor of water at room temperature is of the order of 0. It's some 0.1 of an atmosphere, right? Or 0.01 hundredth of an atmosphere. So it's essentially 0. So it's maybe of the order of 1 kilopascal. And so in other words, if you go up a height which is equal to atmospheric pressure divided by the unit weight of this, so atmospheric pressure is 101 kPa. Unit weight of air is equal to, unit weight of water is 10 kilonewtons per meter cubed. So this is about 10 meters of water. So in other words, if you go up 10 meters, then you'll find yourself all of a sudden that you're at absolute 0 pressure, or close to it, and you'll cavitate. So that's why if you take a 10-meter tube and you suck on it, you won't be able to get water out. You can't suck water out of a well more than 10 meters at a time, well, water, and oil for that matter, because all of a sudden it will cavitate. The only way you can do it is to put a pump at the bottom and to physically pump it up by pushing it, so you compress it from the bottom. And so it's another exposition, if you like, the fact that you'd expect the fluid pressure here to be negative and it would cavitate. So you'd gather bubbles in this particular case. And at this point here, of course, this is the same velocity it's coming out at, v squared over 2g, same velocity. Pressure 0, and the elevation is equal to whatever elevation. So you can use this concept of hydraulic grade and energy line to solve. Sorry, yeah.
I was going to ask that.
Yeah.
You just said.
Yeah, energy line on the top and hydraulic grade line, HGL. So hydraulic grade line. And energy line. Okay, I'm not going to do that. So fine. So a couple of parting shots. Incompressibility. The only term that's important is the fact that in one of the Bernoulli equations, when you develop these equations as we did, you have a term which is 1 over density and pressure. What we do is we take the density outside and do the integration. Of course, that's not necessarily the case. If between upstream and downstream, the pressure is changing in a compressible fluid, and therefore the density changes. And so we did an example, remember, with the closed chamber and the long hose where you had compressible fluid. So we know that we can do it. You just have to take account of the fact that the pressure upstream and the densities upstream and downstream might be different, and therefore you can't necessarily throw them away. So in some cases, we think that we might be able to get away with dealing with incompressibility. Steady states, that means that if you look at the system, it doesn't change with time. What I will do is I will add to this lecture a little derivation to show that you could, if you wanted to, you could take a tank which has a free jet coming out of it. And we know that that free jet would be coming out at some velocity 2. And we've always assumed that the velocity on the surface, v1, is equal to 0. But we don't necessarily need to do that. So what we could do is we could apply Bernoulli to be able to take this velocity, v2, as basically equal to 2gh, where this is the height here. But if it's a tank which isn't a quote-unquote large tank, big tank, which is the kind of code for saying that the velocity on the surface doesn't change because you're not drawing down the level in the tank. If the tank was a small tank and the velocity was finite, then for our coordinate system that we could write, with z going upwards, we could also write the fact that v1 is equal to minus the change in elevation of that water as a function of time. And if we did that, then we could actually integrate this expression to G, let's write it as Z. We could actually take this expression and we could integrate it, and we could figure out exactly what the rate at which this surface dropped. And actually you'd get a very close result to reality. And so it is a steady state expression that we use, but of course you could apply that steady state value incrementally to the different states as this head, as the level in the water tank draws down. And of course from that you could figure out a graph of height of water in the tank as a function of time. And it's not actually very different from looking at well test equations, where you take a well, you put some extra water in the well, and over time you measure how long it takes for that water level to go back down to the initial water level. If you know that measurement of how quickly this water level returns back down to the original water level, you can use to get a magnitude of permeability, which is something we don't talk about in this class, but you will talk about in your other classes. So it seems like a bucket with a hole in it is a very esoteric thing that we're dealing with, but if you think of it as a well with water going out into the well from the well, of course, or doing it the other way, you pull down the water level in the well and allow oil to come in, which is how you produce reservoirs, is exactly the same thing. And so hopefully demonstrating the fact that what we're not talking about in this class is completely esoteric. I think the final parting shot we've already dealt with, and that is frames of reference, which is what we'll start talking about in earnest next time. It's important to choose your frame of reference that is static. And so if you're looking at a submarine, this example just says, don't look at this with a submarine that's moving and static water, which is really the case that you have, because if you have static water at this point and you don't know the velocity at this point, you can't solve it. Instead, transform it so you have a static submarine and water that is moving in this direction, and you can solve this just as we did for the bicycle. So one other thing that can be considered in this is that you can also look at unsteady flows. And so unsteady flows have some relevance in that what you might be interested in, for instance, is how quickly the initial level of this tank drops for it to empty all the way to the bottom. And we know that we can apply Bernoulli to be able to use the equations of a free jet from some location, some height of the system, to the exit point through this orifice. But the question is, can you also use that to be able to say something about how long it would take to empty the whole tank? So that's what we might attempt to be able to do. So if we look at that, let's do this. Then what we could do is try and look at the behavior you get this is Bernoulli, of course. And so the geometry that you might choose would be this tank that would have some form with an orifice in the bottom or the side. We said we could use the side just as easily. And we choose some kind of coordinate system to be able to represent this top. We have a flow line that passes through two locations, location 1 at the top and location 2 at the base. We have a coordinate system which we write in the appropriate way for ourselves, which is positive upwards. And so this would be elevation 1, this would be elevation 2, which we're going to just take equal to 0. And so the question is, how long does it take for this tank to drain? And it's not completely esoteric because it also relates to the behavior. For instance, if you have without getting sidetracked here, if you have a well in a porous medium and you initially have a water level in the well, which is something, and everything's at steady state. This is the water table maybe, and all of a sudden maybe you drop the level of this well, by some amount, so that instead of being here, it is now here, then what would you expect to happen? You'd expect to have flow into this well that would fill it back up to this initial position. And so this happens just to be kind of a diffuse entry into the system, which is kind of this reverse. But if you raise the elevation of this well up to some location, then slowly this would drain down with time to the equilibrium, so that in which case you'd have flow out of the well and into the formation. And so if you measure the time it takes for that to happen, you have some measure of the permeability, which is often permeability. So the permeability is done from a well test, and that's basically the principles used. A bit more sophisticated in the case of this analysis, but the same basic principle. So how do we look at this? Well, what we can do is we can write Bernoulli as usual. So we can write the elevation and pressure at one point and velocity. And we can equate that to the same behaviors at the exit point, where we have elevation, pressure, and velocity at that point. We note the fact that this is atmospheric at this point, this is atmospheric at this point, and therefore we can get rid of these terms because they're both, if we use atmospheric pressure as gauge zero pressure, then they're zero. We have two velocities. Remember when we talked about a free jet, we got rid of one velocity, but in this case the essence of our problem is going to be to include that. So what we'd like to be able to do is we can note the fact that at this free surface, this velocity v1 is going to be equal to the rate of change of the elevation with time. As time gets larger, the elevation will go down because it's going in this direction, and therefore, since the velocity is always positive along a streamline, we perhaps need a negative sign to represent that, but this is what we'd like to be able to represent. So if we can get a velocity that comes out of the bottom of this tank as a function of time, then we could be able to do this. So we should be able to represent the unsteady case. And we can also choose the fact that to be able to do this, we need to represent the fact that we have this velocity of this upper surface, which isn't the same as this velocity of this lower surface, which is what the free jet would be, right? So the free jet equation would be V2 is equal to square root 2g C1 minus C2 in this case, right? But that's only the case where this surface is not moving, and so we need to be able to account for the fact that this velocity is non-zero. So what we can do is we can use continuity. We can use V1 is equal to V1A1 is equal to A2 V2 for starters. And so if we look at what we know here, then we can rearrange this in terms of Bernoulli's expression. And what will we get? If we do it in terms of V1 squared, we'd end up with V1 squared minus V2 squared all over 2g. So what we've done is subtracted this term off to this side, and we have on the other side is equal to Z1 because this is equal to 0. So we have that only. I guess we could multiply both sides by 2g, in which case get rid of this. And so we have a relatively straightforward expression that V1 squared minus V2 squared is equal to 2g C1. It's kind of the components of this, except we have an extra velocity that's still involved here. So what we could do is we could try and get rid of one of these terms, and we could try and write it. It's V1, I guess, that we want to get. So we could try writing V2 in terms of V1. So if we do that, then from continuity, we have that V2 is equal V1 A1 over A2. If we square both terms that we have here, we have v2 squared, v1 squared, and also this whole component here squared as well. And we can use this term for v2 squared to substitute in here. But before we do that, let's just rearrange this expression. So this expression can be rewritten slightly differently if we take v1 squared out. So we have v1 squared, which is the term we want to solve it in terms of, is equal to 1 minus v2 squared over v1 squared. Right? If you just multiply this out, you have exactly the same thing. And the right-hand side is going to be equal to the same. It's going to be 2g times z1. We haven't changed that. And what we could do is we could then substitute this term in here. Actually, we have that exact term, right? We could divide through by v2 squared over v1. We didn't actually need to change that. So this term gets knocked out. And so if we substitute in for this term here, we end up with v1 squared multiplied by 1 minus a1 over a2 all squared. And that's still equal to 2 times gravity times the elevation of the upper surface in any case. And so if you square root that and just rearrange it, we have ultimately that v1 is equal to 2g times z. Let's write it only as z1, doesn't matter, divided through by this term here, which is 1 minus a1 over a2 all squared. This term here. And this would be v2 squared, so we take the square root of that. Make sure we haven't lost any terms in all of this, that this is actually equal to the right magnitudes that we want. I think we have, I think we're okay. And we have an expression for v1. And so what we want to do is now realize the fact that this velocity of this upper surface is equal to this change in elevation with time. So I purposely wrote this not in terms of z1, but I just put it as z. So whatever elevation is at this upper surface, which is what was in our case before. And what we can attempt to do is write this as rate of change of the elevation of the surface with time. v1 is equal to minus dz dt because the surface is going down as time increases and velocity is positive. The only way we can make that the case because of the sign convention for elevation is to have that negative sign in there. And so we have that. And then quite simply what we can do is we can attempt to integrate this. So we'll end up with the terms, so if we write this out as equal to minus dz dt is equal to square root of everything except z in this one, right? 1 minus this term squared multiplied by square root z. So all we've done is we've taken this term outside, which we can do. And if we rearrange that to get all the z terms on one side, we end up with 1 over square root z dz minus, if you like, is equal to 2 times gravity over 1 minus this area squared term, square root, which is a constant, and we have this term left over, which is dt. And so that's the expression that we have. And so what we can do is we can now integrate this between limits. I guess the limits would be whatever we choose to integrate it between. So the limits would be, initially it starts off at z1 at time t1, and it ends up at some other elevation later than that at some later time. And so if we do that that integration, we end up with So this is square root z. This goes to 2 times square root z, just as the integral of that, evaluated between these limits of z1 and z. And the other component we have as being equal to this bracketed term, or sorry, the square rooted term, 2g over 1 minus this squared. And this, the integral of this, of course, is just, well, it is this, right? Is time evaluated between a later time and the initial time, t1, t0. And so if you make those substitutions, you end up with 2 times, well, let's take the 2 out. Let's not do that. Let's divide both sides through by 2. Sorry. So we have that. And so we have the elevation at any particular time minus the elevation at time 1 is equal to a half times square root 2g over 1 minus the areas squared term, and it's going to be t minus t1. t1 is when we start this, so it's equal to 0, times 0 when we start the thing. This is the initial elevation of fluid in the system, and now this is what we want to be able to calculate, so we can just write this as elevation is equal to z1 plus a half 2g, 1 minus, what was it, a1 over a2, a1 over a2 all squared. This is square root multiplied by just time. And so we have some function which gives us an elevation. This should be elevation 1, right? The beginning elevation, whatever that is, plus this magnitude, and hopefully this magnitude is equal to a negative value. And so will that be the case? This is always be positive. A1 has to be larger than A1 always has to be larger than A2, so this will always be a negative number on the bottom, and I haven't kept track of all my minuses, but there should be somehow a minus in here, and this thing should be subtracted off, so this is just doing the same thing. So a minus and a minus avoids the square root problem. I've dropped one of the negatives somewhere, but this is the final expression. So what we can do is we can get the elevation at any particular time as a function of the elevation at the initial time minus some change in that elevation, which is this 1 minus a1 squared over a2 squared square root times time. And so we can be able to show that behavior. So if you plot that out, I think I'd put this together here. Here's this expression. So elevation at time t is equal to square, actually, what did I do? Okay, for some reason, all right, that's the other thing that we need to take care of. So there's no reason that this should have dropped out, right? So these are square roots. So, and so if you want to get the actual value of z, you have to square the whole thing. So if we square this, this is equal to this squared as well. So hopefully that should be the expression that we have. So this is square root of the initial elevation, a half times the square root of 2 times gravity over 1 minus the ratios of the areas, and then the whole expression times time, and then the whole expression squared. So this expression is basically this. And so if you run it for some values, so the elevation of 1 meter, an area of the upper tank of 2 meters, an area of the bottom orifice of 1 meter, then you end up with some result. and you come out with, let's see, what do we get? What do we come out with? We come out with some graph, which isn't quite working. Oh yeah, it's thinking. So it says that it drains in 0.8 of a second, right? So this is the elevation, starts off at 1, comes down. The shape of this curve becomes shallower. You can imagine that's the case because as you have less head, the driving force to make the velocity large decreases, and so the velocity reduces as the head decreases. And so you'd imagine that this kind of flattens out as time goes on. And it looks like by the time it's 0.8 of a seconds, these would be consistent units, 0.8 of a seconds is up, then the tank is completely drained to zero height. And I suppose you can actually calculate, so you can change your values if you want, but you'd calculate whether that is a reasonable magnitude because you know something about this, right? So we know that the velocity at 0.1 at initial time is going to be 2gh square root. H is going to be 1 meter. So you can calculate what the velocity would be from that. So gravity is 10, so it's going to be 2 times 10 times 1 square root. So it's going to be square root 20, which is about 5, right? 25 is 5. 5 meters per second at time 1, which is 0. You know that at time t equals 0.8 from that case, it's going to be, the velocity is going to be approximately 0. And so you know that the average length of time that it's flowing is going to be over 0.8 meters, and the average velocity of that time equals v at t equals 0 plus velocity at t equals 0.8 seconds, halved, which is a fancy way of saying the velocity is 5 plus 0 over 2. So it's about equal to 2. So, you know, square root 20 is about 4. So it's of the order of 2 meters a second average. So if you take 2 meters a second and multiply it by the time, so volume flow rate, total volume is equal to velocity at 0.1 times the area. Total flow rate is times the time. So the velocity average is 2 meters a second. The area is equal to, of the orifice, is equal to 1 meter a second, I think, right? In that expression, what did we use? We used 2 meters for the upper area. The orifice is 1 meter, 1 square meter. Big numbers, of course, crazy numbers, but allow us just to get a handle on this. So the area is 1 meter squared. The time is about 1 second, so 0.8. So it's of the order of 2 meter cubed. And so if you think about the volume of the tank that empties, the area here is 2 meters squared. The height here is 1 meter. And so the volume most definitely is of the order of, well, not approximately, but it's 2 cubic meters. And so this jives with the magnitude of just the average values to some degree. And so what we're doing, I suppose, in that particular case is we're taking the flow rates at, I can't write on this, the flow rate at this point, the flow rate velocity at this point, and we're looking at the average. So anyway, so this gives you a reasonable way of being able to figure out the time taken to be able to drain the tank. So I suppose the other equation we could have done is we could have looked at this average velocity. So we know the initial velocity, and we know the final velocity is equal to 0. So if you know this initial velocity, so we know the average velocity out of the system. We know the volume of the tank, and we know we can convert this into a volumetric flow rate. So if you take the volume of the tank and divide by the vol flow rate, then you should get just the time taken to drain the tank. So the volume of the tank is 2 meters cubed. The volumetric flow rate average is 5 plus 0 over 2, or 4 plus 0 over 2, which is 2 meters per second for the volume. And the cross-sectional area here is 1 meter squared. So the volume flow rate is velocity times area, which is 2 times 1. So 2 meters cubed per second. And if you divide one by the other, you get the time to drain the tank is about equal to 1 second. So not a bad way of being able to estimate this. And of course, not to lose track of the fact that this has the application we talked about before. And the idea would be that you'd take a well, you'd have a portion of it, maybe you perforate portions of that well, so you have orifices where water can flow out, and it has some water level in it. You take that water level and you put some water in it up to some higher magnitude, and you allow it to flow into the formation. As it flows into the formation, this level here will drop. You measure the time between when you start this and the time that you finish this. You measure the volume of this that you pump into it, how long it takes, what this height is, and you can use this to calculate what the permeability is of this, which is some measure of how much effort you have to apply to suck a fluid out of the formation, which tells you how quickly you'll be able to recover your resource. So it's directly analogous to that. Okay? All right. Thanks very much. I'm going to leave that.